All right, let's dive right into this explainer. I want you to picture yourself sitting at that exam desk. The clock is ticking down, the invigilator is pacing the aisles, and you flip the page to a question on the nuclear model of the atom. It looks incredibly easy. You scribble down a quick sentence, you're totally confident you've secured those points, and you move on.
But here's the painful reality of the situation. Imagine looking at your graded paper weeks later and realizing you lost a whole grade boundary, literally dropped a grade because of a simple, totally avoidable mistake on that exact question. I mean, why do so many well-prepared students bleed vital marks on these basic atomic model questions? Well, it usually comes down to the examiner's extremely specific expectations for vocabulary. See, ordinary revision fails because it just focuses on knowing the concept in your head, rather than knowing exactly how Cambridge wants you to actually articulate it on paper. So look at this contrast between vague phrasing and the precise examiner-style wording you actually need to secure top marks. Take the flawed answer. Atoms have a nucleus and electrons. Now, it's not technically wrong, right? But it earns exactly 0 marks in an IGCSE Physics 0625 exam. 0. Now compare that to the top band improved answer. An atom consists of a tiny positive nucleus containing protons and neutrons surrounded by orbiting negative electrons of much smaller mass. You see the difference there? We're explicitly stating the charges, the specific subatomic particles, the orbiting motion, and the relative mass. That right there is how you lock in your marks. Okay, Section 1, Unpacking the Nuclear Model. To avoid those super costly errors, we really need to reverse engineer the absolute core of the nuclear model first. The absolute crucial point here is understanding that the nucleus contains nucleons. Nucleon, it's really just this umbrella term for anything living inside that tiny central nucleus. So, protons and neutrons. We have to rigorously distinguish between the nucleon number, which is represented by the letter A, and the proton number, represented by the letter Z. The nucleon number, A, is your total count of heavy particles right in the center. But Z is strictly your proton count, which is the VIP, because it ultimately defines exactly what element you're looking at. Let's look at some actual data to see how Cambridge expects you to apply those definitions, like instantly. Take lithium. It has a nucleon number of 7 and a proton number of 3. So, to find the neutrons, you literally just subtract Z from A. 7 minus 3 leaves us with 4 neutrons. Boom. We see the exact same logic with sodium. 23 total nucleons minus 11 protons gives us exactly 12 neutrons. Getting lightning fast at this mental math, just doing A minus Z in your head, is honestly your first quick win for the exam. Now, in just a moment, I'm going to show you the exact examiner clue regarding chemical properties that changes absolutely everything. It's a secret that turns those really tricky evaluation questions into guaranteed marks. But actually, scratch that. First, we need to understand the structural framework that makes this clue so obvious. Which brings us to Section 2, Understanding Isotopes and Nuclides. Let's see how all this builds our understanding of elements when their masses start varying. So every specific form of an element is called a nuclide. And when nuclides have the same Z number, meaning the exact same number of protons but different A numbers, they are called isotopes. Think of the proton number as the identity badge of the element, right? It absolutely cannot change. If it does, you have a new element. But the number of neutrons, that can fluctuate, and that gives us heavier or lighter versions of the exact same element. Looking at the 3 stable isotopes of oxygen, notice what stays exactly the same. The proton number, Z, stays completely locked at 8 down the entire list. I mean, if it wasn't 8, it literally wouldn't be oxygen. But check out the nucleons. Oxygen 16 has 16, which means 8 neutrons. Oxygen 17 has 17 nucleons, giving it 9 neutrons. And oxygen 18 has 10 neutrons. So, same element, totally different mass. You might actually be surprised to hear that very few elements consist of completely identical atoms out in the real world. Most are mixture. Take chlorine, for instance. If you scooped up a random sample of ordinary chlorine, you'd find a really predictable mixture. Roughly 3 atoms of the lighter chlorine-35 isotope for every 1 atom of the heavier chlorine-37. Because of this 3-to-1 ratio, if you average out all the masses, chlorine ends up with an average atomic mass of 35.5. Now, while chlorine is a mix, other elements are just heavily dominated by a single isotope. A staggering 99.99% of ordinary hydrogen consists of just the standard H1 isotope. That's just a single proton and 0 neutrons. The tiny remaining 0.01% is made up of its heavier cousins, deuterium and tritium, which have 1 and 2 neutrons respectively. And the physical effects of these isotopes can be absolutely incredible. Just swapping one single neutron completely changes the physical properties. For example, if you bond oxygen with deuterium, which is that hydrogen isotope with one neutron, you create what's called heavy water. Unlike normal water, heavy water is, well, noticeably dense. It freezes at 3.8 degrees Celsius instead of 0, and it boils all the way up at 101.4 degrees. It looks exactly like regular water, but its physical properties are totally altered by just that tiny bit of extra neutron mass.
Moving right along to Section 3, the 4-part examiner framework. Now we can finally unpack that crucial examiner clue we talked about a minute ago.
Whenever you're asked to evaluate, explain, or calculate anything in the 0625 syllabus, you have to rigidly follow these 4 steps to lock in your marks. First up, state the core concept. Second, pull the evidence or data directly from the question itself. Third, apply scientific reasoning to connect that data to your concept. And finally, package the whole shebang in precise examiner wording. So let's apply this right now to solve that open loop we had about chemical properties. Using our framework, the scientific reasoning here reveals the ultimate examiner clue. Just look at this flawed statement. Isotopes react differently because they weigh different amounts. It's such an easy trap to fall into, right? Thinking that because the physical mass changes, the chemical reactions must change too. But they don't. Listen closely to the exact wording you need here. Isotopes have identical chemical properties because they have the same number of orbiting electrons. Boom, that's it. Chemical properties are dictated entirely by the electron shell configuration. Because isotopes of the same element have the exact same number of protons, they also have the exact same number of electrons. Therefore, they react identically. That is the light bulb moment that completely changes how you answer these questions for sure.
Okay, final stretch. Section 4. Avoiding common exam mistakes. Because even with our shiny new framework firmly in place, there are still hidden traps out there just waiting to catch students off guard in the heat of the exam. You've got to mentally audit your answers against this checklist before you flip the page. Ask yourself, are you missing units on your final calculation? Did you round off a decimal in step 1 of a multi-step calculation and just completely throw off your final answer? Did you use vague explanations like, I don't know, the atom gets bigger, instead of the specific term like the nucleon number increases? Always check your graph axes, and please never draw a conclusion that the provided data doesn't explicitly support. Honestly, check for missing units and premature rounding constantly. It is literally heartbreaking to do all the hard physics right, only to lose the mark on a silly math technicality.
So we've built a pretty bulletproof understanding of atomic structure and isotopes in this explainer, but there's still a massive unresolved problem hovering over us. If you face a high mark question on the ionizing properties of alpha, beta, and gamma radiation, the rules of the game change entirely. The syllabus gets much darker, and the mark schemes get way less forgiving. So how are you going to apply this exact same framework to ace those notoriously tricky ionization questions? Definitely something to think about as you continue your revision. Keep that in mind, and I'll catch you in the next explainer.